All right, thanks for coming back, guys. So we're looking at the a couple rules here. First, added additivity of integrals over intervals. That's a tongue twister. The idea here, if we're integrating from, let's get a better pen. If we're integrating from A to B, where C is some value in between A and B, that we can split up those integrals and write it as the integral from A to C plus the integral from C to B. Why does that matter? For this particular example, you wouldn't use it that much, but where it makes a lot of sense, if we were going from A to B here, the C value that we would choose is right here, because that's where our area is switching from being considered a positive area to a negative area. So we'd like to be able to split up those areas, and in fact we're going to use this skill quite a bit in the upcoming sections. So make sure that that idea sort of sticks. We've used this already, but seeing it again. Again, this is a review session of definite integrals, while also adding in the ability to solve them by hand. Okay, similarly, another sort of idea that I think we've looked at before, but should just be made clear. You know, and this is going to seem obvious too, I think. If g is some function that's always bigger than f. So by bigger, we're saying the y value is bigger, and we see that by g being above f. G, from f, g is above it. So the idea is that the integral from a to b of g of x is going to be bigger than the integral from a to b of f of x. Why? Well, I mean, just think about it. It has all this area that I'm shading in now. G has, but f doesn't. And all of this area here, both f and g share. So it makes sense that if g is above f, the area is going to be bigger. Now, while this seems obvious to many, hopefully to you, it's going to be a key rule or an idea that we use when we're finding areas of regions, and we're going to be doing that in the next couple of videos, and I think in 3 videos. So while this is kind of an obvious idea, we're going to be using this theory later on. Okay. Last sort of kind of just a connector, and then we'll do an example problem, and that'll be it. The the idea is where we use the definite integral and the fundamental theorem of calculus the most is when we're integrating some rate. So if we're integrating some rate of change, let's say like the speed that you're going, meters per second, or volume of water, so let's say like liters per second, or population change, let's say people per year. When you integrate that, what you get back is the net change of just the meters that you walked, or the liters of water that have dripped, or the people that have been added. So in other words, when you integrate it, we're getting rid of the unit of time. And we're just looking at the net change of f and no longer looking at the rate. What does that mean? Well, let's look at an example. So we're looking at total sales given a rate of sales. So here's a word problem. It says a company estimates the rate of sales of a given item is given by this following differential equation, or yeah, differential equation. It says, dSdt is the change of sales with respect to time is here, where T is the number of weeks after an advertising campaign has begun. What is the total number of items sold in the first 5 weeks? Well, um, it might be helpful just for us to get a quick picture of what this graph looks like. It's got a 0 at 0. And if we factor this out, another 0 at 12. It's concave down. So this is my derivative, ds dt. And if we're looking at, if we want to know the total number of sales, total number of items sold in the first 5 weeks, it is this area. So if we look at the change of sales with respect to time times time, the resultant is just ds, or the change in sales. That's the theory. The practice says the total number of sales will be the integral from 0 to 5 of negative 3t squared plus 36t dt. And when we integrate that, we're going to get negative t cubed plus 18t squared, and we're integrating it from 0 to 5. So plugging in those limits of integration, when we plug in, that's plugging in 5. When you plug in 0, you just get 0 back. And so what does this equal? I'm going to defer to the trusty calculator. So 18 times 25 minus 125, and we get 325. Okay, so that's the math, but now we need to sort of tie in the theory and the math. So this is by adding up all of the little sales, the rate at which we're selling things. If we add up all of those little rates of selling, so little rectangles here, what we get back, this is the sales after 5 weeks minus the sales after 0 weeks. And we know that the sales after 0 weeks was 0 because we hadn't started selling things yet. So what we found from this definite integral of the derivative is S of 5, the number of sales after 5 weeks. So that's the application. It's an application problem using the fundamental theorem of calculus, antiderivatives, and the definite integral. Take some time to really wrap your head around this idea. It's not too challenging. The algebraic work isn't too challenging, but I think the theory can be a bit tricky.